welcome to part one of our lecture on chapter 6, Understanding and Transforming Raw Scores. So, when you're talking about assessments, we oftentimes get these raw or what we call observed scores on an assessment that by themselves are meaningless without some context for comparison. So, in order for us to understand how someone performs on an assessment, we have to create these comparisons by converting our raw scores into derived scores. And derived scores can be compared to those of a particular group, and we call these norm referenced. We can also establish a criteria or a threshold for an assessment, and we call this criterion referenced scores. Or we can compare someone's individual performance on their current assessment to a previous assessment. And we call this self-referenced performance or derived scores. So here are some examples to help break this down. So if you have someone who is looking for norm referenced scores, you might see how someone compared to others who took the exact same test. You're in school, you take a test in a class, and you get an 80. And it's not an 80%, that's just your raw score is 80. But you want to know how well you did in comparison to other people. So you ask your classmates in class and you look at their scores and they're like, oh, I got a 70, I got a 60, I got a 90, whatever it is, and you compare. That's a norm reference. You're referencing your own score in comparison to other individuals who took the exact same test. Criterion reference might be if you take an assessment and you need to get a certain amount in order to pass. So you need to get 160 out of 200 points to pass. That's criterion reference. There's a specific criterion that you have to surpass in order to know how well you do. And then self-referenced might be if you are trying to determine how well you do on an assessment and you're comparing it to previous tests. So maybe you get a 95 out of 100 on a test in one class and you get an 87 out of 100 in another class. You might compare how well you do in classes and say, well, normally I get about a 93 or higher, so when I get an 87, that's a pretty low score for me. That's self-referenced. You're comparing your own assessment to previous performances. And all of these are examples of how we can take raw scores and convert them into derived scores that provide meaning and context for us to understand what those scores mean. But that's just focusing on us as individuals. Oftentimes, when we are talking about assessments, we need to look at assessments from a much broader perspective. Like maybe we have multiple scores that we're trying to interpret. And when we have that, when we have multiple scores, it can be really helpful and useful to organize our set of what we call raw scores graphically. Because if we can organize those raw scores graphically, it'll be easier to draw conclusions about the overall data distribution beyond what we can glean from simply scanning a list of raw scores. And some of the most common graphic displays of scores are frequency distributions, histograms, frequency polygons, and bar graphs. And throughout our discussion of these organizations of raw scores, I'm going to be referencing this table. So table 6.1, which presents exam scores for 15 classmates. And these scores are going to come up as we talk about all of the different organizations of data. So know that you can also access this table in chapter 6 of our book, and you can reference it while you're going through this. So let's go into a little bit more detail about each of these graphic displays of data. The first of those is the frequency distribution, which is a table with columns that outline the number of occurrences of each score or value, as well as the percentage of a group that possessed each score. So as you can see in this table, our scores, which are in the far left column, which is the score that each classmate got on this test, are typically presented in ascending order. and can be grouped into interval data for clearer presentation. So we get interval data in the F column, which is saying the number of students who achieved that score in the far left column. So you had 2 students who got a 78, 2 who got a 79, 1 who got an 83, 3 who got an 87, and so on. And then in the third column, you see the percentage. This is the percentage of students who in the class received that score. So two students relates to 13.3% of the total class. 1% is one student is 6.7%, and you get the idea. The cumulative percentage in the far right column is showing how many students got to the final score until you reached the entirety of the sample, so all 15 students in the class. So this is a frequency distribution. Shows you the frequency that people achieved each score, and it really presents our data in interval form. So as we discussed in chapter 5, interval data. We also have histograms, which is a bar graph of a frequency distribution. So that the information from a frequency distribution that we just discussed is more visually displayed. In this example, the longer bars in a histogram indicate a higher frequency of that value. So you'll see that the frequency is listed on the y-axis, and your score, your exam score, is listed on the x-axis, with each taller bar indicating that more students achieved that score. Both the x and the y-axes in a histogram are in ascending format, and those individual bars cannot be rearranged. You'll also see that there are empty spaces between some of the bars of a histogram. These are there to indicate that there were no individuals who achieved that score that you're referencing. We also have frequency polygons. And frequency polygons are a line graph of a frequency distribution, with higher peaks indicating greater frequency. A frequency polygon can connect the points at the peaks of values, so both high and low peaks indicate the high and low scores that were achieved based on the number of students who had that score. Frequency polygons are particularly helpful if you have a lot of data and a histogram is going to muddle that. Frequency polygon will smooth out the display of that data. And we also have a bar graph, which is useful for presenting nominal data, and the bars can be arranged in any order for the data presentation. In bar graphs, there are spaces between each data point to highlight that these items are nominal or categorical instead of continuous. So we use bar graphs for nominal data, things that cannot be compared or better than or worse than, but rather is just showing the number of people that were in each category, and each of the spaces between them indicate that these are separate categories. So we have the ways that we display data, but we also need to understand data. And one of the primary ways that we begin to understand data is through measures of central tendency. And these refer to the average score or the value of a quantitative data distribution. We oftentimes use measures of central tendency to help make meaning of the scores that we see in data distribution. There are 3 measures of central tendency: mean, median, and mode. The mean is the arithmetic average score of a data distribution. It is affected by outliers in a data distribution and is typically presented with information regarding a distribution's standard deviation, which we're going to talk about in the next section. The mean is oftentimes used in assessment because it is the one that involves actual mathematical manipulation. So in order to achieve a mean, you are taking all scores in a distribution and you're adding them together. Then you're taking one individual score and you're taking the sum of all of those scores and you're dividing it by the total number of people who took the assessment. And that's going to give you the average of what the majority of people are going to say is how they performed. We also have the median. And the median is the middlemost score, when you arrange scores chronologically in ascending or descending order. So you put them all in ascending or descending order and you take the absolute middle point of that distribution. That becomes your median. If you have two scores that fall within the middle of a distribution, the two values are summed and divided by 2. Although the median helps to address issues associated with outlying scores, the median is not always useful when there is a very narrow or broad spread of scores because it's hard to capture the full complexity of the score or the distribution. And then the final measure of central tendency is the mode, and this is the most frequently occurring score in a data distribution. Distributions can have more than one mode, and that is the case when you have a bimodal distribution or a multimodal distribution where you have two scores that are most frequently occurring. So once you've got measures of central tendency, this sort of leads the path into measures of variability. Because in addition to knowing what the average or typical score is for a data distribution, as assessors, we may want to know what the spread of a data distribution is around that score. So how close or how far apart scores are from one another on average. And really, when we talk about measures of variability, we're looking at a few specific examples. Those include range, interquartile range, and standard deviation. These are the most common measures of variability that will tell us the spread of our data, how close together scores are to one another or how far apart they are. The range is calculated by subtracting the lowest score from the highest score in our range when they're arranged chronologically, and then adding 1 to that number. This is the easiest measure of variability. It's telling you how far apart your scores are. If our scores range from 80 to 20, our range is 61. We also have the interquartile range, and this range helps to remove the influence of any outlying scores by focusing on the data distribution that's closer to the mean, or the median, sorry. So to calculate the interquartile range, you have to divide the scores that are arranged chronologically into 4 parts. So if you have 50 people who take an assessment, or sorry, let's do 100. It's just easier that way. If you have 100 people who take an assessment, you take their scores, all 100 scores, and you arrange them chronologically in ascending or descending order. And you take them and you divide them into sets of 25, and that creates 4 different parts. So you have part 1 is 1 through 25, part 2 is 26 through 50, part 3 is 51 through 75, and part 4 is 76 to 100. And this gives you the 4 different parts that have now been arranged. And in order to get the interquartile range, you are going to subtract the score from the 25th percentile to the 75th percentile. And then you're going to divide that value by 2. So subtract the quarter percentile from the 3/4 percentile and divide that subtraction by 2. And this result will show the range around the median, which is our interquartile range. Interquartile ranges are not used very frequently because they can be a little bit confusing to explain to people, but they are a little bit more robust than the range as it is independently. But the most common, and again, interquartile range is really helpful because it reduces the effect of outliers. But because it is difficult to understand, we have our third measure of variability, which is the most commonly reported measure of variability, and that is the standard deviation. Standard units for standard deviation are calculated for a data distribution by converting the scores to derived scores. So converting raw scores to derived scores. You then convert the mean score on a data distribution to 0 or some other standard score, which we'll talk about a little bit later. And then the standard deviation value then becomes indicative of how many standard units a particular score is on a data distribution. So the higher someone's standard deviation, the greater the spread of the data distribution. So the further apart the scores are from one another. The lower the value of standard deviation, the closer together scores are to one another. And the standard deviation is the most widely accepted measure of variability for test users because it is the basis for standard scores, which we're going to talk about in a little bit more detail. So when we talk about data distributions, these are graphic displays of the measures of central tendency and variability in scores. Data points from a sample or a distribution of scores can be plotted on an x and a y axis, with higher points on a y-axis indicating a greater area or frequency of that particular score or value. And then these data distributions have some important characteristics, starting with the normal curve. So when we're talking about a normal curve, I want you to use this example, that you have a data distribution, and the spread of that distribution is perfectly symmetrical around our measures of central tendency, so that our mean, median, and mode are of equal value to one another, and all scores are perfectly symmetrically arranged around that mean, median, and mode that is all equal. In this state, this normal curve, the data is a bell-shaped curve, which is why we call it a normal curve, when all of the data points are graphed on an x and y axis. All phenomena, if measured an infinite number of times, would approximate this normal curve. So this is what it looks like. It's this top part here where our normal curve creates this bell. That all data distributions are going to fall within this bell. This is a standard normal bell-shaped curve. The mean, median, and mode are all equal at this center point of 0. And in a data distribution, the standard deviation units can provide us with information regarding the percentage of data points that fell within a particular area. So approximately 34% of data points lie between the median and one standard deviation. So you're going to have 34% of people who are between -1 and 0 on the standard deviations, and between 0 and 1 standard deviation, which means about 60% of data points will fall within one standard deviation below or above the median. An additional 14% are found between -2 and -1 standard deviation, and another 14% are between +1 and +2 standard deviation units. And then if we move outside of that, an additional 2% of the data spread can be found both below 2 standard deviation points and above 2 standard deviation units. So we see how our normal distribution of data really displays how the majority of scores in a standard normal curve are going to be around the mean, median, and mode, which are all perfectly said to be at 0 standard deviations because we've converted the mean to 0. This is a normal curve. This is what all researchers and all assessors are looking for, is a standard normal curve. But that doesn't always happen. So when we talk about data distributions, there are some characteristics that don't fall within the normal curve. And when that happens, when scores are not symmetrical around our measures of central tendency, the distribution is known as a skewed distribution. So in a skewed distribution, the location of the distribution in which the most scores fall pulls the distribution in that direction. A pull above the median would indicate a positively skewed distribution, and a pull below the median would indicate a negatively skewed distribution. And the way to keep these straight is that the tail tells the tale, or the tell is in the tail. So when you have a skewed distribution, the direction of the pulled side of the distribution, the tail, reminds us the type of the distribution. The greater the skewedness value, the more lopsided the distribution. So the more scores will fall on the opposite side of the tail. So I have a little sort of way to break this down. So in the middle, we have our standard normal curve, where we have a symmetrical distribution. And then on both the left and the right, we have our skewed distributions. So on the left, you'll see that there is a skew in that a lot of the scores are in the left. But we would say that this is a positive skew because the tail of our distribution, which is right here, is pulled towards the positive side of our x-axis. Then you have the opposite for a negative skewed distribution. The tail is pointing to the negative side of our x and y axis, which tells us that this is a negative distribution. There are some outliers that are very low that are pulling our distribution to a different way than our standard normal curve. So in a skewed distribution, as you can see, the median becomes a better measure of central tendency because it is not affected by the extreme scores. And then within our data distributions, we also have the characteristic of kurtosis, which is a characteristic of a data distribution that refers to the peakedness of that distribution. So given the symmetry of the normal curve, the distribution is characterized as mesocurtic. So when a standard distribution is displayed, it is mesocurtic. It is perfectly displayed, perfectly symmetrical. If you have a data distribution in which the data points are more closely located to one another, you get what's called a high peak in your scores. We call these leptokurtic distributions. And those data points that are flatter across our x-axis are referred to as platykurtic distributions. So again, I have an example to break this down a little bit for us. So a standard normal distribution is going to be this distribution right here. That is mesocurtic. It is perfectly symmetrical. It is evenly displayed as we would expect. When you have more scores that are all close together and close to our measures of central tendency, you get a positive kurtosis, or what we call a leptokurtic distribution. And if you have a much wider spread of your scores, you're going to get this flat plateau. And that's called a negative kurtosis or platykurtic. And I like to think about these as platykurtic as a plateau because they are flattening out like a plateau would. So this is kurtosis, and it has to do with the way that our distribution or our data is displayed. And that's going to be where we're going to leave off for our first part of Chapter 6. Join me for the second part of our lecture on Chapter 6 when we talk about norms, ranks, and the ways that we understand standard scores. I will see you all in the next lecture.